So we are looking at paper 2, which starts off with a practical section. In question 1, we're looking at a diffraction experiment, and we've got a number of dots there, A, B, C, D, and E. And we've done the measurements between some of them as well. So we've got the distance between A and B is A, B and C is B, and then C skips over to E to get our distance C. We've also got a table with some values, and we've been given the uncertainty in the measurements. A lot of the questions are actually about this uncertainty, so I'll probably show you that again. In question 1.1, we're being asked to explain why the student's estimate of uncertainty is different than the smallest division on the ruler. So we're already told that the smallest division, which we usually call the resolution, is 1 millimeter, because over here on this part of the question it does say that the divisions are 1 millimeter. So over here they're seeing that the uncertainty is actually 2 millimeters, and they're asking us to understand what the discrepancy in those two values is in the first case. Now this student, and by the way I will use different students' answers throughout so it's not always the same person, has got a mark because he's noticed that when you use a ruler there's an uncertainty both at the beginning of where you take a measurement and at the end. Now that is literally taking two measurements rather than one, and that's why there are more than one uncertainties that we have to account for here. Okay, so if you've said something along those lines, then you're going to get 1 mark. Where this student hasn't got the second mark, where frankly most of us missed the second mark, is that we didn't say that you have to add the uncertainties. Now that would have got a second mark. What loads of people did is they said that you had to do 2 times the uncertainty. Now if you said this, you did not get the mark. That's because the rule isn't that to combine uncertainties we multiply them. The rule is that we add them, and you can see why you could get confused between those two. So it's essential that you say that you add the uncertainties, so it's the uncertainty of one plus the uncertainty of the other, rather than saying that it's 2 times the uncertainty. Yeah, I get that that is actually the same outcome in this case, but yeah, we need to show that we actually understand the rule. Okay, and this again asks us to show that we know how to combine uncertainties on question 1.2. So it wants to know the percentage uncertainty in the sum of A and B. Now this is quite a crafty question, because usually when it comes to combining uncertainties, for example if we want to combine A times B, or A divided by B, or even A squared, the rule would always be that you would combine the percentage uncertainty in A and add the percentage uncertainty in B. Now that works for all of those. But here we're adding 2 values that have got exactly the same types of units and everything. So actually we don't need to combine percentage uncertainties yet to combine these. We can find the absolute uncertainty just by adding together the 2 absolute uncertainties. So the absolute uncertainty in A plus the absolute uncertainty in B. Now here each of them is 2 millimeters, so 2 plus 2 gives us 4 millimeters. And then you're going to do the absolute uncertainty divided by the value. So you're going to do 4 divided by, well, you've got to come over to your table and add together the value of A and B. Okay, that's going to be 2 divided by 544, which gives you somewhere around about, let's have a look, sorry, just scanning my mark scheme, 0.7. I recommend giving it a 0.7%, because when we're giving a percentage uncertainty we don't normally go more than the first decimal place of a percentage. So I remember telling you that in class. They would have allowed you to do 2 decimal places here, in which case it would have been 0.74. Now, just trying to think what else I need to tell you guys about this really. One of the most common mistakes that was done here and this student has done it, is that they've worked out the two individual percentage uncertainties and combined them. But yeah, here we need to find the absolute uncertainty first. If you've gone for this method here, I am allowed to award you 1 mark because you've shown that you do know how to calculate a percentage uncertainty, even if you've made a mistake in how you do it for 2 items summed together. Okay, so remember, step 1, find the absolute uncertainty by adding the uncertainty of A to the absolute uncertainty of B. Secondly, turn it into a percentage uncertainty by dividing it by the actual value, and yeah, times by 100. Where a lot of people lost marks was the rounding as well. Make sure that you round it to no more than 1 decimal place, really. Like I said, they would have allowed 2 in this case. Okay, now this student hasn't answered 1.3, and personally I thought 1.3 was a pretty tricky one, so I kind of get it. It says, discuss why the experimental measurements lead to a different percentage uncertainty in C compared to in A and B. In my opinion, the easiest way to answer this is remembering that the percentage uncertainty is going to depend on the absolute uncertainty. And if you're going to do A and B, there are 2 lots of the absolute uncertainty, whereas here there's only 1. Perhaps one good solution is to actually calculate it, and that will get you a mark. So here we can do 2 divided by our value for C times 100. It comes out about 0.37%. You can compare it to what you got in the previous one. Now, many people said that the error for C was smaller than the error for A and B. I can only actually award you the mark for correctly saying that if you remember to say it's the percentage error in C that is smaller than the percentage error in A plus B, because of course the absolute error was the same in all of them. It was 2 millimeters. Okay, so you must say the percentage error in C is smaller than the percentage error in A plus B. And then for that second mark, there's a few ways you could have got it. You could have maybe done that calculation, show what the percentage error in C actually was, or you could simply have said that finding C required fewer measurements, it required taking fewer readings. Okay. Right, let's come on to 1.4, which you guys did really well. It was an excellent selection of results. The most commonly used one was to use less reflective surfaces. I mean, you know, we did this practical in school and you guys all did that right then, so I'm happy to see you got that. I would really like you to please go and have a look at the mark scheme and cast your eye on the right hand side of the answers to this question, because there's a little bit that says weak answers should be ignored, and it's really interesting to see what they consider to be a weak answer. For example, something like do not look at the laser. I suppose that's a weak answer because you can look at the laser, you just can't look down the laser beam. So yeah, just quite interesting to sort of spot that as a bit of English language stuff going on there. Okay, let's come over to here. So here we've got a diagram of from top down basically of what we saw earlier. The first question I thought was an absolute gimme, really friendly. We're being asked to work out theta. Now we can do that because we know the adjacent angle and we know the value of the hypotenuse as well, C, which of course you've been given over here. And just be a little careful because one's in meters and one's in millimeters, okay? Now I've got to say, far too many people got this wrong. So we're just going to say tan to the -1 of this over that, opposite over adjacent. Okay, now that should come out as 23.0 degrees. If you gave more significant figures, you had to make sure that it rounded to 23.0. If it rounds to anything else, you can't have the mark. I saw some people using sine, for example. I saw some really strange answers I didn't even understand, and certainly there were some rounding errors. So please take care because you lose all the marks, even though you basically know what you're doing. Okay, so on to 1.6. Spot E is the second order maximum. Okay, that's useful for the equation that we're going to use. And we're being asked to calculate the wavelength of light. Now, okay, I saw quite a few types of error come from this question. So the first thing is we actually need to select the right type of equation. because this is one of the equations that we can use when we're looking at diffraction, but this is for double slit, so we need to use a different equation, specifically the n, where n is the number of orders, and we've been told here that it is the second order. Lambda, wavelength, which is what we're trying to find, equals d sine theta. Now we've just worked out sine theta. And the thing that's caused the most problems is this d. If you use the equation, you rearrange it, and you accidentally for d used that this value here, 3 times 10 to the 5 lines per meter, then at least you're going to get one of the 2 marks available. So this caused a lot of people a lot of problems. You can see that this student here has also taken d to be 3 times 10 to the 5. The trouble is, d is the slit separation. So if there are 3 times 10 to the 5 lines in every meter, be careful, they usually give it in every millimeter, then you need to do 1 over the number of lines per meter. And that will tell you how wide the separation of one of the slits, okay? And if you do that, you should come out with a value of lambda of about 6.5 times 10 to the minus 7 meters. Right. There's one last question here as part of 1. So in this question, the student plans to repeat the experiment using basically the same equipment. Now this is a question we addressed quite thoroughly during the lesson, and some of you guys have got a mark here. A couple of you got both marks. So let's see what's going on here, because this student has got a good suggestion. If we want to reduce the percentage uncertainty in sine theta, well, there are actually 2 ways to do it, but for me the most obvious one, we need to increase the value of theta. Sorry, that's not actually what I mean. We need to increase the values of y so that we can get an increased value of c, because c is what we're measuring with a ruler, remember. So if we can make c bigger, and remember that percentage error is the uncertainty, absolute uncertainty divided by the value. So the absolute uncertainty is going to stay the same because it's still a ruler and we're still measuring there at both ends. It's still going to be 2 millimeters. If we can make the actual value bigger, then the percentage uncertainty is going to be a lot smaller. So the trick is move this further away. So that is increase y. That will of course produce a larger value for c. But to answer this one, exactly what the student has said, please. Increase the distance between the diffraction grating and the screen. It might be helpful to actually say this is distance y, just so you're making sure they know what you're talking about. But the reason why the student hasn't got a second mark for this is just because they need to say this will reduce the percentage uncertainty. Okay, so yeah, that's question 1. If you've got any more questions about this, make sure you pop them in the posts on Teams.